So for the class today, what I was planning was to go over a couple of practice problems that I prepared here, which would be hopefully a good review of things for the semester. The first of these problems is related to perturbation theory, so it follows up on what we've just been doing, also on the harmonic oscillator, so it's kind of review about that topic. And the second problem is related to spins and successive measurements. All right, so let me get that out here and I'll connect the iPad, just a second. Okay, so we're sharing. What? I get this message, a software update is required. What is this deal? Okay, it must be because I upgraded to the iOS 4.5, 14.5, whatever you call it. Okay, well, here it says downloading, 24 seconds remain. Let's see if that really works. Okay, I hope so. Need that. All right, so the first one is problem 7.2 from the textbook in the chapter about perturbation theory. And so I believe I assigned 7.1 and 7.3 in the latest homework. So here's 7.2. Okay, is this going to work now? Let's see. Come on. All right. Do you see it here? Is that working? Okay, good. Okay, so here's the question. All right, for the harmonic oscillator, we have the certain allowed energies, okay? And so you know all about that from when we were working on the harmonic oscillator. Okay, so now suppose the spring constant increases a little bit. So for example, suppose we cool the spring so that it becomes stiffer than it used to be. Okay. This now is a problem that we can solve in two completely different ways. One way to solve it is exactly. That is, we can find exactly the new energies because we have a new harmonic oscillator problem with a different value of omega. Okay. The second way is using perturbation theory. That is, we can say the extra stiffness of the spring is like a perturbation on top of the old harmonic oscillator potential. Okay, and so want to solve it both ways and check to make sure that the solutions come out the same if we do it both ways. Okay, so let's try it first in the exact way, which is actually pretty easy. Okay, so if we do that, all right. Here, I hear some interference on the line, and I don't know if that's coming from me or somebody else. Is anybody else unmuted? No, no. Must be coming from me. I wonder why. That's really strange. Okay, well, let's see if it persists. I hope not. All right. No, I heard it again. That's really weird. All right, let's see what we can do. So for the old unperturbed problem, V of x is 1/2 kx squared, or in quantum mechanics, we usually write that as 1/2 m omega squared x squared. Okay, so omega is the square root of k over m. And we know the energy levels then. So we know the unperturbed energies, the E superscript 0 for unperturbed, subscript n, those are n plus a half times h bar omega. Okay, now the new problem has v of x is 1/2 of 1 plus epsilon times k x squared. Okay. So we could write that as 1/2 m omega nu squared x squared. Okay, so omega nu is the square root of the new spring constant k, 1 plus epsilon k divided by m. Okay. So now we want to know what are the energy levels associated with the new problem. Okay. Well, the exact solution is actually kind of trivial. Okay, the exact solution is that E sub n should be n plus a half times h bar times the new omega. This is n plus a half times the old h bar, the old omega, times the square root of 1 plus epsilon. Okay. This is an exact solution. There is nothing wrong with it. Okay, and it was actually pretty easy. Okay. Now, suppose we just want to care about how does this depend on epsilon, right? So if epsilon is something really small, the change in the spring constant is really small. Whoops. So we could ask, how does the exact solution depend on epsilon? I am really sorry about all this noise here. Let me just check the settings for my audio just to make sure anything didn't get disrupted. So built-in microphone. Well, I'll change my microphone. Can you hear me now? It's all right? But it's the same noise. Oh, well, that's not good. I don't know why that's happening. That is really weird. Well, can you tolerate it if I just go on? All right. Okay, let's see what we can do here. I'm not sure if I can tolerate it. Well, I'll do my best. Okay, how does the exact solution depend on epsilon? All right, so we have the epsilon, excuse me, the E sub n is the one, it's the n plus a half h bar omega times the square root of 1 plus epsilon. Okay, so that is something which we could write as a power series in epsilon if we want to. Okay, so there's a power series for the square root of 1 plus epsilon. And that power series is 1 plus a half epsilon minus an eighth epsilon squared plus dot, 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 like that. Okay, so, this is the standard Taylor series. If you just expand this thing the way you've learned about in calculus classes. So this tells us then that the energy is n plus a half h bar omega. Yikes. The energy is n plus a half h bar omega, right? That part has nothing to do with epsilon, plus n plus a half h bar omega times a half epsilon, minus n plus a half h bar omega times an eighth epsilon squared. Okay. So this now looks like a perturbation series, right? It looks like this piece is the old unperturbed energy, and then this thing is the first order perturbation, and this thing is the second order perturbation. So it looks as if this is the sort of thing that we could have gotten from a perturbation theory. Okay. So let's try it. Let's try studying this problem using perturbation theory and see if we get the same answer. Okay, that's the goal of this problem. And of course, no one would really do it this way, in real life, because we have an exact solution available to us. But let's just try it just for practice and see if it's all consistent. Okay. I'm going to try one more thing with my sound because I'm so annoyed by it. I'm going to stop the iPad sharing for a moment and see if that stops things.
Yeah, I was going to say, Professor, that it's happening every 30 seconds, almost to the dot. So it might be it sounds like a connection issue.
Okay, I will disconnect the iPads and I'll reconnect it. Maybe that's what makes the trouble. Okay, so here I'm doing it without the iPad. I'm not hearing the noise. I'm not hearing the noise. If I go back to my internal microphone. Okay, I'm still not hearing the noise. Okay, so let's try putting the iPad back in again. Okay, so it's connected but not sharing. I'm not hearing the noise. And then I'll do the sharing. Okay, you see it. I don't hear the noise yet. Maybe it's all right. Maybe disconnecting and reconnecting makes it better. Okay, I hope so. All right, so now this is part B of the question. Nope, there it is again. Huh. That is so weird. I have no idea what's going on, but I need to continue. All right, so the question asks us now, calculate the correction to the energy and see what we get. Okay. So let's do that. Whoops. So using perturbation theory. Okay, so whoops. B, using perturbation theory. Okay, so the old potential energy was this V of x is 1/2 kx squared. And the new potential energy is V of x is 1/2 1 plus epsilon times kx squared. Well, we could say that's 1/2 kx squared plus 1/2 epsilon. Whoops, kx squared. Yikes. Okay. So we could say this is the old potential energy right here, and this is the perturbation. Okay, so we could say the perturbation, this is what we've been calling H prime, the change in the Hamiltonian. Okay. So we want to know what does this perturbation do to the energies? Okay, so we have formulas for that we've derived this week. Okay. So the first order change in the energies is like this. It's E1n, which is the expectation value of H prime in the old unperturbed state. Like that. Okay, so we want to calculate what is this expectation value. Okay, so one method for calculating this expectation value is to do an integral, right? That's the usual way we would get an inner product like this. So that means we would do an integral so we would say that inner product is an integral minus infinity to infinity. And we have our function psi n of x complex conjugate times the H prime, which is 1/2 epsilon kx squared, times the wave function psi 0n of x dx. Okay, we could look up what is this wave function, the old unperturbed wave function. That's some Hermite polynomial times an exponential function. Okay, and then do this integral, right, using whatever integration software you like. Okay, this would give us an answer. Okay, but the question asks us to do something trickier than that. Okay, so if we look at the question, it says, hint, it is not necessary. In fact, it is not permitted to calculate a single integral in this problem. Okay, hint, hint. That is because the textbook authors want us to do a tricky solution using raising and lowering operators. So let's try that. So method 2 is with raising and lowering operators. Okay, so that, let me remind you about what we know with raising and lowering operators. Okay, so you remember when we were doing the harmonic oscillator, we found that there were these two operators. Okay, so A plus is 1 over the square root of 2h bar m omega negative I p hat plus m omega x hat. And a minus is 1 over this square root positive I p hat plus m omega x hat. Okay, so if we want a clever way to figure out stuff about x, we can just add these two equations. Okay? So if we add those equations, we find that a plus a minus is 1 over the square root of 2h bar m omega. Then the p parts cancel, and we're just multiplying by 2m omega x hat, the position operator. Okay, so this is the square root of 2m omega over h bar times the position operator. Okay, so turning that around, we see what is the position operator in terms of a plus and a minus. Okay, the position operator is h bar over 2m omega a plus a minus. Okay, so that means we know what the position operator does when it operates on any of the old states. Okay, it has one piece, a plus, which raises the state, and it has another piece, a minus, which lowers the state. Okay. So the position operator acting on one of the old states, psi n, this is the square root of h bar over 2m omega. And then there's a plus acting on that state, plus a minus acting on that state. Whoops. Okay, now what do a plus and a minus do to that state? Okay, well, a plus acting on the state gives you something times state n plus 1. Okay, what's the something? Well, I had to look it up in the chapter. It gives you the square root of n plus 1 times the state psi n plus 1. And a minus acting on that state gives you the square root of n times state n minus 1, like this. Okay, now what is x hat operating twice? Okay, so x squared acting on psi n, that means it operates twice, okay? And so that is x operating on what we just found, h bar over 2m omega square root of n plus 1 psi 0 n plus 1 plus square root of n psi 0 n. Okay, so let's do it again. Okay, let's let x operate again. So now it's h bar over 2m omega. Okay, so n plus square root of n plus 1. So a plus acting on psi 0 n plus 1 plus square root of n plus 1 a plus, no, a minus acting on psi 0 n plus 1. Okay, so that's x hat operating on the first term. Okay, for x hat operating on the second term, it's root n a plus acting on psi 0 n plus root n a minus acting on psi, whoops, this is an n minus 1, n minus 1, psi 0 n minus 1. Okay, is that good? Did I make any other mistakes I haven't quite yet? Not yet. Okay. All right. So now a plus acting on n plus 1. That's the square root of n plus 2 psi 0 n plus 2. Okay. This a minus acting on psi 0 n plus 1. That's the square root of n plus 1 psi 0 n. A plus acting on psi 0 n minus 1 gives us a root n times psi 0 n. A minus acting on psi 0 n minus 1 gives us this root n minus 1 psi 0 n minus 2. Okay, so now we can make the expectation value. Okay, so now we can say our expectation value of x squared. Oops, yeah. All right, the expectation value of x squared, right? So here, maybe I better copy this and paste it. Okay, so this is x squared acting on psi 0 n is like that. Okay, so I'm going to copy that and paste it to the next page. Copy, okay. And if I go to the next page and paste. Okay, so now if I want the expectation value, that's the inner product, psi n x squared psi n. Okay. So that is h bar over 2m omega. So I'm going to let the bra psi n act on everything. Okay. In the first term, when the bra psi n acts on it, that bra is orthogonal to the ket psi n plus 2. So the first term gives us 0. In the second term, when the bra psi 0 n acts, it gives us a 1, right? When it is combined with this ket. Okay, so for the second term, we get this n plus 1. Okay, now for the third term, when the bra psi 0n acts on this, right, it gives us a 1 right here, acting on this ket. Okay, so we have to add on plus n. Okay, and for the fourth term, when the bra psi 0n acts on this ket psi 0 n minus 2, those things are orthogonal. So we get 0. Okay. So this expectation value is h bar over 2m omega times 2n plus 1. Okay. So this is, the same thing that you would have gotten by doing the integral, okay? But with this tricky algebraic method using the raising and lowering operators. Okay, so that means we can say, what is the first order change in the energies? Okay, so the first order change in the energies, the first order change in the energy En. Okay, so that is this expectation value of H prime in the state psi 0n. That is the expectation value of 1/2 epsilon kx squared in that state. So the factors of 1/2 epsilon k come out, and the expectation value of x squared is this thing that we just calculated. And then we have 2n plus 1, like this. Okay. So can we simplify this, right? Well, let's see. K is m omega squared, right? That's this k. Okay, so this is multiplying h bar over 2m omega times 2n plus 1. And so the m's cancel, one of the omegas cancel, and we get 1/4 epsilon h bar omega times 2n plus 1. All right. Or we could write that as 1/2 epsilon h bar omega n plus 1/2. Okay, so this is our first order change in the energies. Okay. Now let's go back and compare it with what we got with our other method. Okay, if we saw how does the exact solution depend on epsilon, okay, well, there's a first order change right here, and that's the same thing that we just calculated. Okay, so perturbation theory is consistent, right? It gives the first order expression for how the exact solution depends on epsilon. Are we good with this so far? Yes, okay. What about the second order term? Well, we have a second order perturbation theory, so let's try it out. Okay, so to test our second order perturbation theory, we have an equation for what is the next highest order, next lowest order, the next term in the perturbation expansion. Okay, and so that is that the second order term in En is a sum over all possible states other than the state we started with of this matrix element, psi n h prime psi m divided by this square denominator, which is the difference of energies. Okay, so now we need to calculate what is this matrix element that goes into the numerator. So for that matrix element, we want to say, let's calculate this psi n h prime psi m. Or that's just the complex conjugate of psi m h prime psi n. Okay, I wrote it this way because we already know about h prime acting on psi n. That's what we figured out already. Okay, so this is 1/2 k epsilon times psi m acting on x squared acting on psi n. Okay, but we know this thing, x squared acting on psi n. That's what we figured out right up here on the top of this screen. Okay, can I still paste it? No. All right, I'll copy and paste again. So if I copy and paste this thing, oops. Copy. Paste. Okay. So now if we want psi m to act on this, okay, so let's let the bra psi m act on that ket that's up here, right? This sum of kets. Sum of kets. Okay. When can it be non-zero? Okay. It is non-zero if m has to match one of the kets that's right here. Okay, so m has to match n plus 2 or n or n or n minus 2. It has to match one of those things, otherwise you'll just get 0. So it's non-zero if m equals n plus 2 or n minus 2. Those are the only non-zero cases, okay? So we can evaluate it, right, in each of those cases. And in fact, we don't even need the case where m equals n, because we have a sum here for m not equal to n. So we only need the cases where m is n plus or minus 2. So if m is n plus 2, then psi n plus 2 acting on x squared, acting on psi n, is the stuff right up here multiplying this psi n plus 2. Okay, so that is h bar over 2m omega times square root of n plus 1, n plus 2. Okay, if m equals n minus 2, then this expectation value that is what's multiplying this ket right down there. Okay, so that's h bar over 2m omega square root of n times n minus 1. Is this sort of clear for you guys? If anybody has questions, please just ask me, okay? All right, so that tells us then, these are the only non-zero terms, okay? So even though this sum, could in principle be a sum of an infinite number of terms, really only 2 of them are not 0, okay? So let's figure out those 2 terms. Okay, so if I copy this, right, so here in this sum, I just need to add up 2 possible values of n. Okay, so this is, if m equals n plus 2 or n minus 2. So psi, this is n plus 2 squared E0n minus E0n plus 2. And then the same thing with n minus 2. Okay, so let's work all this out. Okay, so we have all the information we need. Okay, so for the first term, okay, we want the absolute value squared of something. Okay, the thing that we want there is the 1/2 k epsilon, all that stuff has to get squared. 1/2 k epsilon times this business right here. Okay, so this business right there. So h bar over 2m omega times this square root of, it's n plus 1 times n plus 2. Okay, and all of that is divided by the difference in energies, right? So the energy for state n minus the energy for state n plus 2. Okay, so that's h bar omega times n plus a half minus h bar omega n plus 2 plus a half. And then in the second term, we have all the same kinds of things, a half k epsilon, h bar over 2m omega, and now it's a square root of n times n minus 1. So this all squared in the numerator, and in the denominator, it's h bar omega n plus a half minus h bar omega n minus 2 plus a half. Okay, we good so far? All right. So this is, well, here, I'll square this stuff now. Okay, so in the numerator, let's see, we have a fourth squared, so that's a 16th, k squared, epsilon squared, h bar squared over m squared omega squared times n plus 1, n plus 2. And all of this is divided by negative 2 h bar omega. Then, what else? Well, we need to add the same stuff, 1/2 or 1/16 k squared, epsilon squared, h bar squared over m squared omega squared, n minus 1, all divided by 2 h bar omega. Okay, so we're actually almost done. Just have to simplify that a little bit. Okay, so this second order change in the energies, let's see. So 1/16 k squared. So 1/16 k squared is m squared omega to the 4th. Now what? Epsilon squared h bar squared divided by m squared omega squared. Okay, and then what? So that's a prefactor in each of those terms. Okay, and now what? We have a denominator of 2 h bar omega in all of the terms. Okay, and now the first thing is negative n plus 1, n plus 2. And then positive n minus 1. Okay, so let's see if we can simplify this. The m squareds cancel. There's an omega cubed in the denominator, omega fourth there, so it's omega. The h bar factors cancel. Okay, so this is 1/32 h bar omega epsilon squared, and then all the factors in brackets. Okay, so negative n squared minus 3n minus 2. Okay, just multiplying out the first thing. And then plus n squared minus n. Okay, so the n squareds cancel. So this is equal to negative 1/32 h bar omega epsilon squared, and then 4n plus 2. Or negative 1/8 h bar omega epsilon squared n plus a half. All right then. So this then is our second order change in the energy. And we can compare that with what we found a long time ago. Right here. Okay, right here, that this is the second order change in the energy. So that's all consistent. Now, of course, this is a really artificial problem because nobody would really do all the work of doing perturbation theory when you can solve the thing exactly just like this, right? But now that, it gives us practice with perturbation theory. So now you could do the same calculation if the perturbation were not some extra x squared potential, but you could do it if it's an x cubed potential or an x to the fourth potential, right? And so you could say, what if your simple harmonic oscillator is not so simple, right? What if the potential energy has a little bit of x to the fourth in it? How does that change the simple harmonic oscillator states? Okay, that problem we could solve by just the same method, okay? And so the point of this is just to have practice with the method, right, rather than really to solve this particular problem. Okay. So this problem, incidentally, this is harder than I would actually put on the final exam, right? I mean, this is something that's more work, but a problem very similar to this was on the physics PhD candidacy exam this spring. And so, in general, we would say, a difficult problem for undergraduates is equal to, I won't say an easy problem for graduate students, but a doable problem for graduate students. And so this is something that, PhD students were expected to do on a test. Okay, but you guys know the method, and so it is tractable that way. Okay, so that was one of the problems that I prepared here as practice in perturbation theory and practice in the simple harmonic oscillator. Okay, there's a second one that I also prepared that's a little bit shorter. So let's go through that. This is also a problem from the physics PhD candidacy exam. So also, something that I would regard as kind of a challenging but doable problem for this course. All right. At the beginning of an experiment, an electron is in this spin state, okay, right here. Okay, so it is 4/5 times the up state plus 3i over 5 times the down state. Okay, so the up state means the state with s equals a half and m, or m sub s equals a half. And the down state means the state with s equals a half and m equals negative a half. So suppose we measure the spin in the z direction. What is the expectation value of the spin in this state? Well, we have experience with that sort of problem, okay? So this is the kind of problem that we can solve using a matrix method, okay? So with the matrix method, we know that our state psi, the question writes it as 3/5 of the up state plus 4i over 5 times the down state. Okay. We could equally write that as a column vector, 3/5 4i over 5. Okay. And the corresponding bra is 3/5 times the up bra minus 4i over 5 times the down bra, considering that you remember when you switch from a ket to a bra, you need to take the complex conjugate, okay? So that I changes to negative I. Or we could write that as a row vector, 3/5 minus 4i over 5. Okay. We can check the normalization. The question doesn't ask for this, but it's always good to be careful and make sure that whoever wrote the question didn't mess up. Okay, so this combination, right, this is the inner product of psi with itself. So this is 9/25 plus 16/25, which is 1. Good, check, that's fine. All right, so now that we're confident that it's normalized, we can calculate expectation values, okay? So if we want the expectation value of S sub z, that S sub z operator corresponds to a matrix H bar over 2 times the sigma sub z matrix, which is +1, 0, 0, -1. Okay, so the expectation value of SZ in the state psi, that's the inner product of the psi bra with SZ with the psi ket. So that is 3/5 minus 4i over 5. And then the SZ operator, H bar over 2, 1, 0, 0, -1. And then the ket, 3/5 4i over 5. Okay, so we just have to multiply this out. Okay, so if we do the matrix multiplication, the h bar over 2 factors out. And let's see, I'll copy this row vector and I can multiply the matrix times the column vector. So that's 3/5 plus 0. And on the bottom, it's 0 minus 4i over 5. So if I multiply this out, it's h bar over 2. And let's see, 3/5 times 3/5. So 9/25 minus 16/25. And that is h bar over 2 times negative 7/25. Okay, now this actually disagrees with my notes. So what did I do wrong? What did I do wrong? Ooh, I copied the question wrong. Yikes, I copied the numbers wrong there. Oh. All right, I can fix that. Sorry about that, you guys. Okay, so this, I got the 4s and the 3s backwards. Stupid. Okay, so I get partial credit. Okay, this is a 4, this is a 3i. Okay, let's fix that. Let's fix that. 4/5. This is a 3i. Okay. Yeesh. I'm so distracted by all the extra noises. I'm not paying attention to copying the numbers right. Okay, so this thing, -4/5, negative 3i over 5. 4/5, 3i over 5. Okay, this is still 1. Good. Okay, so now if I fix it here, there. Okay, this is 4/5, negative 3i over 5. This is 4/5. This is 3i over 5. Okay, down in there. 4/5, negative 3i over 5. And then this thing is 4/5, negative 3i over 5. Okay, so that is 16/25 minus 9/25, which makes h bar over 2 times plus 7/25. So that's 7 h bar over 50. Okay, that agrees with my notes. Yes, excellent, good. So that's part A. Okay, part A, good. Part B, suppose we measure the spin, SZ, in the Z direction, and we observe SZ equals plus h bar over 2. What is, after the measurement, what is the spin state of the electron? We do not need any calculation to solve this part, right? To solve this part, we just say that the nu psi is the eigenstate that corresponds, the eigenstate of the observable SZ, which corresponds to the eigenvalue h bar over 2. So that eigenstate is 1, 0, or equivalently, it is up. Okay, so we are just, because we measured SZ, we go into an SZ eigenstate. And this is the corresponding SZ eigenstate. Okay, that is part B. Part C, after the measurement in part B, we measure the spin in this direction, the n hat direction, where n hat is z hat cosine theta plus x hat sine theta. So n is some vector in the xz plane. What is the expectation value of the spin in that direction? Okay, so we need to know the state and the operator. Okay, so we want to calculate the expectation value of Sn. That is in the state psi nu. What is Sn? We know what is psi nu. That ket is 1, 0. The corresponding bra is 1, 0 also. Okay, but what is S sub n? Right, well, S sub n, right? If we have a vector in any direction n, that is n dotted with the vector of spin operators, so the vector of s's. So the same way that S z is z dot the vector of spin operators, and Sx is Sx dot the vector of spin operators. So Sn is n dot the vector of spin operators. So that means it is nx Sx plus ny Sy plus nz sz. So n sub x in this question is given as sine theta. Sx is h bar over 2, 0, 1, 1, 0. Ny is 0. Sy, well, it doesn't matter, but it's 0 minus I, 0. Nz is cosine theta. Sz is h bar over 2, 1, 0, 0, minus 1. So if we add those things up, we get a matrix, which is h bar over 2, cos theta, minus sine theta, minus sine, plus sine theta, plus sine theta, minus cosine theta. Okay, so we want to know the expectation value of Sn in that state. So psi nu Sn psi nu. Okay, so that is 1, 0, then h bar over 2, the matrix, cos theta, sine theta, negative cosine theta, then 1, 0. Okay, so this is, I factor out the h bar over 2 and do the matrix multiplication. This is cos theta times 1 plus sine theta times 0, cos theta. Okay, and on the bottom, sine theta times 1 minus cos theta times 0, sine theta. So this is h bar over 2 times cosine theta. Okay, and then for the last part of this question, so here what we found was h bar over 2 times cosine theta. Okay, this is Sn. Okay, now what are the limiting cases of Sn in the limits of theta equals 0 and theta equals pi over 2? Okay, so if theta equals 0 means that Sn is h bar over 2 cosine 0. So that's h bar over 2. If theta is pi over 2, Sn is h bar over 2 times the cosine of pi over 2. That's 0. So discuss whether these limits are physically reasonable. Right? Well, here the idea is, we should think about what's the question and what do we expect the answer to be. Okay, so if theta equals 0, that means n is in the z direction. Okay, so n is in the z direction. Okay, so what's happening in this question is in part B, we measure the spin in the z direction. Okay, we observe plus h bar over 2. Then in part C, we measure the spin in the z direction again. Okay, right? Part B is a measurement in the z direction, and part C is also a measurement in the z direction, assuming that theta equals 0. So if we measure the spin in the z direction and we get h bar over 2, and we measure the spin in the z direction again immediately afterwards, we're going to get h bar over 2 again, right? Because we have collapsed the system into the state with the spin sz is h bar over 2. Okay, so it makes sense that the expectation value of this Sn is h bar over 2. Okay, what about the other limiting case? If theta is pi over 2, so that means that n is in the x direction. Okay, so in part B, we measure the spin in the z direction. We get spin up in the z direction. Then in part C, we measure the spin in the x direction. What's the spin going to be in the x direction? I don't know. It's equally likely to be plus x or negative x, right? We put it into a state that's aligned in the z direction, and now we make a measurement in the x direction. It's equally likely to be plus or minus. So the expectation value of the spin in the x direction is 0. And that's what we've just calculated in that limiting case. Okay. By comparison, if we measure the spin in some diagonal direction that's partly z and partly x, then we'd say, well, it's more likely to be in the up part than the down part, because our n direction is sort of aligned with z, not perfectly, but sort of. And so that's why we would get an expectation value of h bar over 2 times the cosine of theta, right? So a number between 1 and 0 if theta is between 0 and 90 degrees over here. Okay, does that sound sort of reasonable for physical interpretation? All right, that's my second problem. Okay, so with that, I am out of time and I will stop, and I'll see you guys on Monday for a final class to wrap things up for this semester. And you'll have a homework for me on Monday also. Okay, so long, you guys. See you on Monday.